Good morning students, I am Aravindan, Assistant Professor, Department of EEE, St. Joseph College of Engineering. Now I am going to take a topic on DC machine. What are the construction of the DC machine, how the DC machine works, how the DC machine can be used as a generator or motor, and what are the different types of DC machines, that is what are the different types of generator and what are the different types of motor. Now initially first you have to know what is a machine. The machine is nothing but, here in this DC machine you can able to operate the DC machine as a DC generator or a DC motor. That is, here the energy conversion happens here. That is, one form of energy is converted to another form of energy. What are the two types of energy conversions here means? If you are going to take it as a generator, basically the generator will convert mechanical energy into a electrical energy. If you are going to consider it as a motor, it will convert electrical energy into a mechanical energy. Here in this DC machine, you are going to give a supply as a DC supply if it is a motor, or if it is a generator you have to get the output as a DC output. Here in the DC machine you should know one important point, that is this DC machine construction wise it is same for generator as well as the motor. And moving on to the construction of the DC machine, this DC machine will have two parts, generally two parts. One is stator, it is a stationary part, and second one is rotor, it is rotating part. Okay. Here the stator, stationary part, is static in nature, and rotor, rotating part, is dynamic in nature. Here in this DC machine you will be considering the pole core and pole shoe with the field windings as a stator part, armature and commutator as a rotor part, where it will be driving, that is it will be dynamic. Moving on to the construction, in the construction we will be having various parts in a DC machine. The parts of the DC machines are yoke, field winding, and pole core, pole shoe, and then armature, armature teeth, armature winding, armature core, armature slot, brush, shaft, and commutator. These are the various parts of the DC machine. First we will go from the outer part to the inner part of the DC machine. The outer part of the DC machine has yoke. Yoke is nothing but it is a casing of the DC machine. It is a casing of the DC machine. That is a protective part of the DC machine. That is the yoke. And this yoke will protect the field as well as the armature, that is stator as well as the rotor of the DC machine. And also you will be having some slots over it where the heat dissipation will also happen. Now we will move in detail about the stator and rotor of the DC machine. In stator, the stator is nothing but it is a stationary part. Stationary part has field windings, pole core and a pole shoe here, and also the brush is also a stator here. Okay. Now, here you will be having the field winding which will be given a DC supply is wounded over the pole core. Here it is a pole core, this is a pole core, wounded over a pole core. The field winding is wounded over a pole core, and you will be having a pole shoe here where the field winding will not be present. Why this construction is like this? Should have a question. See here, this pole core width is small and hence the requirement of the copper conductor will also be low. If the pole core and the pole shoe length width is very high, then you require a more amount of copper conductors and it is not economical. That is why you will be having like this. But by having this pole core with very small, you can't able to extend the linking of flux from pole core to armature. That is why you require one more part of the pole, that is pole shoe, where the wide area or wide width or wide cross sectional area of the pole shoe will link the magnetic field produced by the pole core to the armature conductors. Okay. Now, here you should know one thing, how the flux is going to be produced in the field winding. That is, assume that you are going to have an iron piece. In the iron piece, you are going to wound the copper or aluminum conductor, and if you are going to give a supply to this copper or aluminum conductor, this iron piece will act as the electromagnet. What is the difference between a permanent magnet and electromagnet means? The permanent magnet is a magnet which is always magnetized. But in electromagnet, whenever you are going to give a supply to the winding, this iron piece will get magnetized. If you remove the supply, then this iron piece will be demagnetized. Okay. Okay. Now, we have discussed about some magnets, right. What are the properties of magnet? The properties of magnets are, the magnetic lines of force will flow from north pole to south pole, that is you know it, outside the magnet, and inside the magnet south pole to north pole. Always the magnetic lines of force will have a closed path, and all the students will be knowing it, that is unlike poles attract, like poles repel. That is, if it is a north pole and north pole, it will repel. If it is a north pole and south pole, it will attract. And no magnetic lines of force will intersect with each other. Okay. These are the main properties of the electromagnet or magnet or electromagnet. Okay. Now, our aim is to make this machine to work as a motor or generator. Okay. And by giving the excitation to the field winding, the field which is going to be excited produces the field which is called as a main field. That is, in the field winding, if you are going to give the supply to the field winding, you will be producing the flux or field which is called as a main flux. Okay. And now we are going to give a supply to the field winding. The field get excited. Excited means the magnetic property is produced in the pole core and pole shoe, and that will link the armature conductors. Here this pole, here we have assumed the 4 pole machine, 1, 2, 3 and 4 pole machine, and north pole and south pole, south pole, alternatively you will be having the poles of the DC machine. And this field produced in the pole core and the pole shoe will link the armature windings. Now this armature winding and armature is acting as a rotating part, that is a rotor of the DC machine, and armature has various parts which has armature core, armature tooth or teeth, and armature winding, and then armature slot. This is armature slot. See here, the armature has some areas projected and some areas not projected. The projected area of the armature is called as armature tooth or teeth, and the part which is not projected is called as the armature slot. Okay. Now here you will be having the armature winding which is placed over the armature slot. In the teeth you will not have any kind of armature winding, only in the slot you can able to place the armature winding, and that armature winding will be wounded over the entire length of the armature. Here we have seen the 2-dimensional image of the DC machine. If you are going to see the generic machine in practical, you can able to see the winding wound like this. Okay, it will have a closed path. Here this circle represents the armature winding which is placed over the slot, and this armature winding, if it is excited, then it produces the armature winding produces the armature flux. It produces the armature flux. Now, when this armature flux will be produced, how this armature flux will be produced, that differs the DC machine with generator and motor. In a DC, if you are going to consider this machine as a DC motor, our input should be a electrical input and output should be a mechanical output. What is the electrical input? Where you can able to give the electrical input in this DC machine? See, already we have told that the field winding will always be excited. There is no change in the field winding excitation, it has to be excited, either it may be a motor or it may be a generator. But armature winding plays a major role, where this it will tells whether this machine is a motor or generator. If the armature winding gives the electrical output, then it is a generator. If the armature gives a mechanical output, or if the armature takes a electrical input, then it is a motor. Okay. Now, we are going to consider this DC machine as the DC motor. And how it is going to operate as a DC motor? Here this DC, in this DC machine, now this DC machine is going to be considered as the DC motor. In a DC motor, input is electrical input and output is mechanical output through the medium of magnetic field. Through the medium of magnetic field. See here, where you will be giving this electrical input to the DC motor means you have to give the electrical input in armature windings. Armature winding. Okay, you are going to give a electrical input to the armature winding, and you will be getting the output, mechanical output, as a rotation of the armature, as a rotation of armature. How this rotation is going to happen? You are going to consider a two permanent magnet which has a north pole and south pole, okay, and this north pole and south pole is nothing but is a field winding. You are going to excite the field and that field will produce the main flux. That main flux or main magnetic lines of force will links the magnet, so which links the north pole and south pole from that is the magnetic lines of force will move from north pole to south pole. Now, how the mechanical rotation is going to happen with the electrical input to the armature winding? In between you are going to have, in between the north pole and south pole you are going to have armature. Okay. This armature has a armature winding which is placed in the slot, and that armature winding when it is excited, that is, if you are going to assume that you are going to give a supply to the armature winding into the plane of paper, assume that is a cross, okay, then this armature will produces the magnetic lines of force in clockwise direction as a concentric circle. Okay, as a concentric circles. Here, and these lines will be flowing in a clockwise direction. In a clockwise direction. Here you can able to see that this part of flux is aided, and this part of the flux is opposing each other. Opposing each other. Therefore, the net flux here, the net flux is lower or decreases. Here, the net flux increases, okay, because it is aiding in nature and it is opposing in nature. Now, see here, this armature is over a shaft, it is placed over the shaft, and this armature can't able to move here and there because of the variation in the flux density. Okay. Now this armature can able to rotate only because it is above the shaft. Therefore, how the rotation will be made means, the rotation will be made from high density area to the low density area of flux and low density area to high density area of flux. If it changes, what happens? Then the rotor will rotate. You are giving an electrical input to the armature winding and you are going to get the rotation of the rotor as the output. Rotation of the rotor as the output. Okay. Now, you should know one thing, that see here, you are going to have this teeth and slot. This teeth and slot is not in a smooth surface. Here you are going to have a projected area and unprojected area. Therefore, the air gap between the field poles and the teeth of the armature is low, and this air gap between the slot and the field pore is high. Here the reluctance between the armature teeth and the pole shoe is low, reluctance between the slot and the pole shoe is high. Okay. The reluctance is nothing but the resistance of the magnetic field. When the distance increases, the reluctance increases. Then the distance decreases, reluctance decreases. When the reluctance decreases, the linking of flux will increase. When the reluctance increases, the linkage of flux will decrease. Okay. Now you can able to understand how the DC motor works, that is by giving an electrical input, how the mechanical output is produced, that you can able to understand it here. Now you are going to consider this machine as the DC generator, this machine as a DC generator. The DC generator, in DC generator you will be having the input as mechanical input and output as electrical output. The generator will be getting an electrical output through the medium, that is a DC generator. Okay, DC generator. Here the DC generator, the input is mechanical input and output is electrical output through the medium called magnetic field. Now, if you are going to study about the generator, you should know first one is the Faraday's law. Faraday's law of electromagnetic induction. What is Faraday's law of electromagnetic induction? It is whenever there is a change in flux with respect to time, then the EMF will be induced in a particular conductor. EMF is nothing but is a potential. Whenever there is a change in flux with respect to time, EMF will be induced in a particular conductor. Now, why I am telling this point here means, see here, you are going to have the armature here, and for this armature you have to give the mechanical input. You have to give the mechanical input. How you will be giving the mechanical input? The mechanical input will be given through the prime mover, and where the prime mover will be connected, the prime mover will be connected to the turbine of the generator. Initially you will be having a turbine, and this, assume that this part is a turbine and this part is a armature. Here you will be having some blades. Okay, in a turbine you will be having the turbine blades. High pressure steam or water, if it hits the turbine blades, the turbine will rotate. If the turbine rotates, the armature of the rotor will also be rotated. How it will be rotated? This turbine shaft is connected to the DC machine shaft, that is DC generator shaft. Okay. Both are interconnected or interlinked. When this turbine rotates, what happens? The prime mover which is connected between the turbine and the rotor of the generator will also be rotated. Like this you can able to give a mechanical input to the generator. Now you have given the mechanical input to the generator. Our aim is to produce the electrical output. How you can able to produce electrical output here means based on the Faraday's law of electromagnetic induction. That is, whenever there is a change in flux, at every instant of time EMF will be induced in a particular conductor. See here, now I am giving the supply to the field winding. The field winding is excited. If it excited, what happens? The pole core and the pole shoe will be electromagnetized, and since because of the electromagnetism, what happens? The flux will be produced and the flux will link the armature conductors. Since the air gap between the teeth and the slot are uneven and the armature conductors are placed in the slot, what happens means the linking between the linkage of flux, that is a main flux linking the armature conductor, will change at every instant of time whenever it is rotated. Okay. When it is rotated, what happens? There will be a change in the flux linkage between the stator and the rotor, and because of the change in flux linkage, EMF will be induced in a conductor. Where the EMF will be induced means the EMF will be induced in the armature winding. Okay, in the armature winding. That is what here the Faraday's law of electromagnetic induction represents. Now, how that output of the output electrical quantity will appear means, see here, since it is rotating in nature, the output electrical output will be alternating in nature. With respect to time, the induced EMF produced will be alternating in nature. But this should not happen, right? Because we are studying about the DC machine. In a DC machine, you should not get an alternating output. You have to get a direct output, that is direct current or direct voltage, you have to get it as a output. So, you have to convert this quantity, that is alternating quantity, into a direct quantity. How you can able to convert this? Means you can able to convert the alternating quantity into a direct quantity by means of the commutator and brush arrangement. The commutator and brush arrangement, how it will happen? The commutator is rotating with respect to the armature, because commutator and armature are interconnected with each other, but the brush remains stationary. Assume that you are going to have a single turn coil. Okay. you are going to have a single turn coil and you are going to have a brush here. It represents a positive polarity and it represents a negative polarity. The commutator will rotate, which is connected with the armature winding, will rotate, but the brush remains stationary. Brush remains stationary, and hence the polarity will remains in a unidirectional format. The brush remains stationary. Polarity of the brush will not change. Polarity of the brush will not change, and hence you can able to get a direct output. Okay, and all these entire structure is placed over the base of the machine. Base is nothing but is the bed of the machine. Okay, where it should be stubborn and it has to withstand the rotating system with the robust construction. Okay. Now you can able to see the overall construction of the DC machine. That's the DC machine has the various parts and how the DC machine can operate as a motor and generator. Okay, as a motor as well as on the generator. Now here in a generator you can able to generate the EMF, right? That EMF is called as the generated EMF, that you will be representing it as EG. How this EG is going to be produced? Okay. Now I will explain it how the EG is produced. EMF generated in a generator. EMF generated in a generator. See here, EMF generator, you all know that according to the Faraday's law of electromagnetic induction, according to the Faraday's law of electromagnetic induction, we know that E is equal to d pi divided by dt. Whenever there is a change in flux at every instant of time, EMF will be induced in a particular conductor. Here now for a simple calculation of the EG, we are going to take one revolution of the armature conductor. That is, for one revolution of armature conductors, the flux linkage or the flux produced over the poles P is equal to pi into P, and time taken for 1 revolution equal to 60 divided by n, where n is a speed in rpm. Okay. Now, what is this? Induced EMF. Induced EMF equal to d phi divided by dt, that is d pi is pi into p here and dt is 60 by n. Therefore, you can able to write E equal to pi into p divided by 60 by n, that is the generated EMF Eg equal to pi p n divided by 60. Now, okay, till now we have discussed about the EMF generated in a generator, that is Eg equal to pi p n divided by 60. Actually, we have considered for a single conductor. Now, you will be having a one conductor connected in parallel and finally it is in series. If you are going to add all those things, if you will be having this ratio, that is Z by A. Z is nothing but number of armature conductors, and A is nothing but number of parallel path. Okay. If you are going to multiply this with the Eg, this is a final generated EMF for the entire system, that is pi p n divided by 60 into Ez by A. Okay. Now, here I have mentioned two things. One is Z as a number of armature conductors, that is armature conductors, how many number of armature conductors are present in the machine, and A is nothing but number of parallel path, how the parallel path will be produced, that is placement of armature conductors represents the number of parallel path. Okay. In a number of parallel path, based on the number of parallel path, you will be having two categories. One is lap winding and wave winding. Okay, lap winding and wave winding. If you are going to take the armature conductors as a lap winding armature conductors, you will be having a overlap of armature conductors over it, that is you will be having a overlap of armature conductors. Okay. Overlap of armature conductors. If you are going to take it as a wave conductor, wave winding, then that is when a wave, the number of parallel path will be equal to 2, that is progressive winding. But in lap winding, the overlap happens where A is equal to number of parallel path equal to number of poles. Okay. If you are going to substitute for Eg as a lap winding, then for lap winding Eg will be equal to, that is A equal to P. Okay. This P and P gets cancelled, pi n A divided by 60, sorry, Z divided by 60. If it is a wave winding, Eg will be equal to pi p n Z divided by 120, that is 60 into 2. Okay, that is for a lap winding and wave winding. Now, what are the difference between lap and wave winding means? The first difference is the winding will overlap with each other and number of parallel path will be equal to number of poles. In wave winding, it is a progressive wave where the number of parallel path will be equal to 2, and in lap winding, it can able to withstand high current and low voltage, but in wave winding, high voltage, that is the machine can be used for high voltage and low current machine. The machine will be, if the winding is armature winding is lap winding, then it will be having a high current and a low voltage device, and then if you are going to have a wave winding, it can able to have the withstand the high voltage and low current device. Okay. Now, we will be discussing about the back EMF. Okay. What is a back EMF? The back EMF will be produced in the DC motor. How that back EMF will be produced? First, we know that in a DC motor, the output is mechanical output. Okay, the output is mechanical output. And how the back EMF is going to be produced? That is, after a motoring action, this rotor is going to be rotated, armature is rotated. After this rotation, what happens? Because of this rotation, it cuts the flux produced in the field winding, that is a main field, and there is a change in flux at every instant of time linking the armature winding. Because of it, the back EMF is produced. The back EMF will oppose as the cause producing it, that is, it opposes a supply given to the motor. Okay. That is what the back EMF represents. The back EMF is basically the EMF produced in a DC motor, where after a motoring action there comes a generating action. Because of that generating action, the EMF is produced in the armature winding. That EMF is called as the back EMF. This is what about the overall idea of the construction of the DC machine, and what are the different parts of the DC machine, and how the DC machine can act as a generator and a motor, and what are different types of windings present in the DC machine, and what is the generated EMF of a generator, and what is the back EMF of a generator, back EMF of a motor. That is what we have discussed till now. Now, we are going to study about the different types of motors and generator. What are the different types of motors and generators? That is, first we will discuss about the DC generator. DC generator. The DC generator is classified into two categories based on the excitation, that is, separately excited and self excited. Okay, in a self excited we will be having further 3 categories: DC shunt, DC series and DC compound. Okay, now in the DC compound we will be having further 2 categories: cumulative and differential compound. Okay, now our first aim is to draw the electrical circuit of the generator, DC generator. How we can able to draw the electrical circuit of the DC generator? Okay, first we will discuss about the DC separately excited DC generator. Generator. Okay, in a separately excited means here you are having 2 windings. One is field winding and another one is armature winding. Yes, armature winding. Okay. Supply voltage given separately for the field winding, and it is armature winding where you will be produce generated EMF. Okay, generated EMF, and it is given to the load where you will be having the terminal voltage. Okay, terminal voltage, and the current flowing in the field winding is taken as IF. Current flowing in here is taken as, the load is taken as IL, and the current from the generator is taken as armature current IA, and armature resistance RA is present. Okay, if you are going to write the electrical equation of this system, then here you can able to write applying KVL, EG equal to terminal voltage plus IA into RA plus the brush voltage. Okay, where here IA equal to IL, IA equal to IL, and second is self excited. Okay, it is a separately excited, and second one is self excited. I'll draw the self excited machine. Self excited machine, DC self excited generator. In a self excited generator, first one is DC shunt generator. Okay, how we are going to draw the self excited DC shunt generator means here you will be having the generator, armature and field, and then we will be having a load. Okay, here you will be having the generated EMF EG, RA, and the current flowing from the armature is taken as IA towards the field is taken as ISH because shunt field, and towards the load is taken as IL. Terminal voltage is taken as VT. Okay, it is the electrical circuit of a DC shunt generator, where if you are going to write the electrical equation, that is the KVL of this system, you can able to write EG equal to VT plus IA into RA plus V brush. Okay, but see here how we are giving this direction, that is the direction like this: IA, ISH, IL. They have upward direction, downward and downward direction. Why we are giving this direction means, see here in a generator the electrical energy is produced and it will be given to the load. Okay, therefore this prime mover, okay, it is given to the turbine. Okay, turbine is connected to the armature, and when the turbine rotates, armature will also rotate and produces the electromagnetic field EMF, and that potential, when it forms a closed path, it flows as a current towards the load. So from the generator the supply will be given to the load, that is why the current direction is like this. And also you can able to tell that higher potential to lower potential. Here this generated EMF is a higher potential and the load is consuming the lower potential. That is why the current is flowing like this. Okay. Now if you are going to write the electrical equation or KVL equation for the system, you can able to write EG for this loop. EG equal to terminal voltage VT plus IA into RA drop, that is armature winding drop, that is IA into RA plus V brush. Okay. This V brush is sometimes negligible. Okay. Now you can remove it, that is EG equal to VT plus IA into RA. Okay. Now what is this IA? IA equal to ISH plus IL. Okay. And what is this? ISH equal to VT divided by RSH. Okay. This is what about the DC shunt generator. Moving on to the second category, DC series generator. Second one is DC series generator. In a DC series generator, the field winding is connected in series with the armature. That is generated EMF RA, current from the generated EMF is taken as IA, okay, and current towards the field is ISE, and the field resistance is RSE, current towards the load is taken as IL. Okay. Now for this circuit you can able to write the KVL equation, that is EG equal to VT, that is the terminal voltage, VT plus IA into RA plus ISE into RSE, where IA equal to ISE equal to IL, because all are in series. IA is equal to ISE and ISE is equal to IL. Now you can able to replace it like this: EG equal to VT plus IA into RA plus RSE. Okay, and also IA is equal to IA equal to ISE equal to IL. Okay, you can include the breast drop also. Okay, if you need, if they are in the problem, if they are given breast drop, you can include the breast drop also. Okay. Now this is what about the DC series generator. See here, you can able to visualize, that is here you will be having a thick winding, okay, but here you will be having a thin winding, but the number of turns in this winding is high when compared with that. Okay, why? Because means here this RSH, that is here you will be having RSH, okay, RSH, that is resistance, is very high. RSH is high here, but here RSE is very low. Okay. If you are going to increase this RSH, then the entire current will be given to the maximum amount of current will be given to the load, and the load will be satisfied. If this RSE is very high, then what happens? The entire supply will be having a drop here, and the remaining amount of voltage will be appeared across this load. That is why the RSE is very low and the supply will be given to the load in a efficient way. Okay. And this RSE is having a thick winding when compared with the RSH. RSH has a high amount of resistance, RSE has a very low value of resistance. Okay. And the third one is DC compound generator. Okay. In a DC compound generator, based on the construction, you will be having long shunt and short shunt. First, long shunt. Long shunt generator. Okay. Shunt is nothing but you are going to have the shunt field winding connected between the series combination of series field winding and armature. Okay. See here, long shunt represent, you will be having a series field winding and then you will be having a armature winding, and over it you will be having a shunt field winding, and then you will be connecting it with the load. and this is Eg. Ra is a armature resistance, Rse, and the current flown from this Eg is taken as Ia, current flown towards this Rse is taken as Isc, current flown towards this Rsh is taken as Ish, and current flown towards this load is taken as IL. That is, long shunt is nothing but, long shunt is a shunt field winding connected with parallel or across the series combination of armature and series field winding. That is why it is called as a long shunt. Okay. Now, if you are going to write the electrical equation of the system, then if you take this loop, okay, Eg equal to, and here you will be having the terminal voltage, okay, Vt plus Ia into Ra drop plus Isc into Rse drop, okay, and here Ia is equal to Isc because both are in series, okay, and Ia is equal to Ish plus IL, okay, and then Vt, sorry, Ish equal to Vt divided by Rsh. Okay. Now we can replace this part Eg equal to with this equation, okay, Vt plus Ia into Ra plus Rse, okay, you can replace the equation like this. Now it is all about the long shunt and short shunt. Second one is short shunt. In a short shunt, you will be having the series field winding and you will be having the armature, but the shunt field winding will be connected only across the armature, then it is called as a short shunt, okay, then it is called as a short shunt DC generator. That is Eg, Ra, Rse, Rsh, and if you are going to write a current direction, Ia, Ish, Ise, IL, okay. Now write the electrical equation, okay. If you are going to write the electrical equation of the circuit, Eg equal to terminal voltage Vt plus I A into Ra plus Ise into Rse, okay. Now here Ia equal to Isc plus Ish and Isc is equal to IL, okay, Isc equal to IL, okay. Now here we can able to see that Eg equal to terminal voltage plus the drop Ia into Ra plus the drop Isc into Rse, okay, where Isc and IL are in series. That is why I am taking this Isc equal to IL, and then Ia is equal to ISC plus ISH by using KCL. Okay. This is what about the electrical equations of DC generators. Okay. Now, similarly you can able to write it for the DC motor. I will discuss that. In a DC compound generator, based on the connection you will be having long shunt and short shunt. Based on the excitation you will be having two categories, one is cumulative compounded and differential compounded. In the cumulative compounded, compound generator is nothing but you are going to have two field windings. Okay, one is shunt field winding and another one is series field winding. If both the flux are aided each other, then it is called as a cumulative compounded generator. If both the flux are opposites or opposes each other, then it is called as the differential DC compound generator. Okay. Here the field winding increases, cumulative compounded field winding increases, differential compounding the field winding decreases. Okay. Here the field winding decreases. That is all about the basic idea over the DC generator. Okay. Now, we will discuss about the DC motors. This is all about the DC generators. Now, we will discuss about the DC motors. In the next class, we will discuss about the DC motors. Thank you.